section 6.8 is another word problem section. It's a little bit trickier than 6.7 because it doesn't deal with money. You may or may not have seen these problems in intermediate algebra. I have these problems in my intermediate algebra text thing that I wrote, but I don't cover them. So you may or may not have seen them. If you have or haven't, you're not going to be at an advantage or a disadvantage. They're not going to be too bad. The first few problems in this section start off with a short little sentence, and in that sentence is an equation and words that tell me what that equation can be used to model. And the first few problems just want us to get used to these, we call this exponential growth equation. First of all, the letter in the equation, not the e, because e is like pi, it's like 2.718. The letter in the equation is in the exponent, so I would call this an exponential equation. Because the number to the left of the letter is a positive number, I call this an exponential growth equation. If the number next to the t was a negative, I'd call it an exponential decay. But because the letter to the right of the equal sign is in the exponent, it's an exponential function. Because the number to the left of it is positive, this is exponential growth. Because this formula is talking about the world population, and the world population is growing as opposed to getting smaller. For something that was getting smaller, I have like exponential, could have exponential decay. A little bit later on, we have like half-life problems. Like if I had 100 grams of uranium right now, uranium is unstable in nature and it decays. And if I wanted to say, you know, how much uranium am I going to have in 5 years, the amount, the 100 grams is going to be less in 5 years than it is now because it's decaying. That would be an exponential decay problem. And the equation for the uranium growth, next to the t, which stands for time in the exponent, there would be a negative number as opposed to a positive number. So if the quantities are increasing, the number next to the t in the exponent is going to be positive. If the quantity is decreasing over time, the number next to the t in the exponent is going to be decreasing. So once we start to use this formula, we'll get comfortable with how it works. But most of the problems that we're going to do in this section, we're going to either be given a formula in this form, p of t equals some number times e to some power, or we're going to create that formula. It's always going to be the case that the number to the left of the e is the somehow beginning amount, and that's what question A wants to do. So this formula says t equals 0 represents the population in 2012, and question A says what's the world population in 2012? To find that out, I'm going to use the formula, and I'm going to put 0 in for t because t equals 0 stands for 2012. The number to the left of the e is the answer that you get when you plug in 0 for t. So for part A, I'm going to plug in 0 for the t's and get p of 0. P of 0 means the population in year 0, and here year 0 is 2012. And I'm going to do this on my calculator. I'm going to go 7.2 and then second in ln and then 0.0117. I didn't put the 0 to the left of the decimal place because it's not needed, times 0. And when I hit enter, so I wrote 7.2, hit second in ln, I have an e and an up arrow, and then 0.0117 times 0. I hit enter, I get 7.2. It's always the case that when you plug 0 in for t in these exponential functions, that you get the number to the left of the e. This is considered like the initial, I'd call this the initial population. But in this particular problem, what is the world population in 2012? The world population is 7.2. Well, it's definitely more than 7 people in the world. And this parenthetical comment up here said the world population in billions. So this 7.2 means 7.2 billion people. So I'd say that there are 7.2 billion people in the world in the year 2012. And I imagine that's reasonably close to correct. I'm not sure if I took this problem from another text or not, or if I just looked up some numbers on Wikipedia to make my own word problem. That's probably what I did here to get some realistic numbers. The next thing it asks, what's the growth rate in world population? Probably don't need that S there. Always in the exponent, the number to the left of the t in the exponential growth function is the decimal version of the growth rate or decay rate. So this 0.0117, that's the rate at which the world population is growing as a decimal. To make that into a percent, I'm going to move the decimal 2 places to the right. I'm going to get 1.17%. So the growth rate, this says the world population is growing at a rate of 1.17% per year. Now, that's not like in a country like Belgium or Japan, they actually have negative growth. And if I was just doing this for one country, the growth rate wouldn't be that. If you went to some place in sub-Saharan Africa, the growth rate might be like 15 or 20%. And in a place like Belgium, it might be like -3%. But averaged out through the entire world, the growth rate is 1.17%. And that's always going to be the case, that the rate at which the function is growing is going to be the number to the left of the t. If it's negative, it means it's getting the population is getting smaller. If it's positive, it's getting bigger. Next thing I want to do, part C, is estimate the world population in 2015. That's similar to part A. I'm going to plug a number into the formula for t and get a value that represents the world population. And for this particular problem, if I plug 0 in, I'd be getting the world population in 2012. If I plug 1 in, I'd be getting the world population in 2013. If I plug 2 in, I'd be getting the world population in 2014. I want the world population in 2015, so I'm going to plug 3 in. I'm going to go P of 3 equals 7.2 times e to the 0.0117 times 3. I'm just going to do that on my calculator. So I'm going to go 7.2 second ln 0.0117 times 3. Close out my parentheses. Again, I don't know how well you can or can't see that because of the horrible glare that we get here. But that I just typed that in on my calculator, and it says, again, it says round to the nearest whole number. Oh, I'm going to change that to round to one decimal place. I don't like this round. I'm going to write 7.5 billion people as opposed to 7 billion people. So let me say round to the nearest, round to 1 decimal, and I'll make a note to myself to change that. And I'm going to round 7.45 to 7.5 billion people. So I'll say there's going to be 7.5 billion people in 2012. That's the easy part of number 2. The first 2 I could get without algebra, because plugging in 0, you always get the number to the left of the exponent. The number next to the t in the exponent changed into a percent is the rate at which the function is growing, in this case the world population. And to estimate a population, I'm just putting a value in for t. The next 2 parts, if there are 2 parts, are going to be harder. I'm going to need that formula, so I'm going to write that formula down again, because that's going to be relevant. So the formula says P of t, the world population, can be found by taking 7.2 times e to the 0.0117 t power, where t equals 0 is 2012. The question is, when will the world population be 12 billion? When it says when, that means I'm solving for t. What I'm going to do is I'm going to change the population, the left side of the equation, to 12 billion, and 12 will stand for 12 billion. So to do part D, I'm going to put 12 billion in for the world population and solve for t. A little bit messy to solve. I'm going to have some rounding to do. First thing I'm going to do is divide both sides by 7.2. And then I'm going to take the ln of both sides. On the left side, when I divide 12 divided by 7.2, I'm just going to carry 3 decimals worth of accuracy. Well, I get 1.66. I'm going to write 1.667. And that's maybe not the best thing to do, because the earlier you round, the more magnified the effect of your rounding is, and the farther your answer is from the exact answer. But I don't want to carry all those decimals, and I don't want to write that. I actually could make that into a fraction if I hit math, enter, enter. Probably would be better if I used 5/3, but I'm not. I'm just going to use decimals and live with it. Now I'm going to take the ln of both sides and leave the left side the ln of 1.667. If you did ln of 5/3, it would be better. On the right side, I'm going to make the exponent a coefficient using the power to product rule. So I brought this in front of my logarithm. The nice thing about doing this, because the ln of e is 1, this is really the ln of 1.667 equals 0.117t times 1. I forgot a 0 there. Too many zeros going on. So I get the ln of 1.667 equals 0.0117t. I'm going to divide both sides by 0.0117. On the left side, I'll be left with my t, which is going to be my answer. And on my right side, it's purely calculator. So ln of 1.667 divided by 0.0117. And I get 43.67, 43 point, it says round to the nearest year. I don't mind that so bad. I get 43.68 years from 2012. And I'm going to round, because it says round to the nearest year. That doesn't seem so offensive as in the first part. Well, so it has to be 43.68 years, or I'll say in 44 years if I'm rounding to the nearest year. But that's 44 years from 2012. So if I asked you when's the population going to be 12 billion and you say in 44 years, that would be a correct answer. Another thing that would be correct, if you just take the year 2012 and add 44, you'd get in the year 2056. That would be a better answer. I would take either of these. If you said in 44 years, that's rounded to the nearest year, or if you said in the year 2056, they're both correct because it's currently 2012. I guess if in 2015 these videos still exist, which I imagine they do, I don't think I'll record new ones for 3 or 4 years, then probably 2056 would be a better answer. But I'd take either relative to this problem. Next, there's another part. How long will it take the world population to double? So I know that the current population from part A is 7.2 billion. To double 7.2 billion, I multiply it by 2, and that's going to be 14.4 billion. So this is asking me when the world population will be 14.4 billion. I have to have that formula handy, that formula that said P of t equals to 7.2 times e to the 0.0117t. And what this wants me to do is plug in 14.4 billion for the world population and solve for t, for how long. And it'll tell me how many years. I can tell you when it's going to be. So I'm going to go 14.4 billion equals 7.2 billion times e to the 0.0117t. I'm going to divide both sides by 7.2. That's easy for me to do. That left side's going to be 2. I'll get 2 equal e to the 0.0117t. I'm going to take the natural log of both sides. I'm going to leave the left side just the natural log of 2. On the right side, I'm going to make the exponent 0.0117t a coefficient of, so I'll break this in front of my logarithm. Just like in the other part, this piece is equal to 1, so it can go away. So I get the ln of 2 equals 0.0117t. Now I'm going to divide both sides by 0.0117. On the left side, I need calculator. On the right side, I'm going to get my answer because I'm going to be left with a t. So it's just going to be the natural log of 2 divided by 0.0117. And when I do that, it says round to 2 decimals. I get in 59.24 years. I'm really inconsistent with my rounding here. So the answer is going to be the world population will double in 59.24 years from 2012. And if I add 2012 plus 59.24, I'd say kind of in the year 2071. So during the year 2071, 59.24 years from 2012 is the year 2071, and even you guys will be old then. So that's everything that's asked for problem 2. And I take either of these answers for 2E, just like I would accept either of the answers for 2D. If you gave me the number of years or the physical year, I'm content with both of them. They're equivalently correct. 4 is the same style of problem, where it gives me an equation that models something that, and it's an exponential growth equation. It's an exponential equation because the letters in the exponent, the population is growing because the number to the left of the t is positive. So this is considered an exponential growth word problem. And immediately, this word problem says this function will give me how many insects there are in a population in t days, where 0 is the beginning number of insects. Guaranteed that in this problem, there's going to be 500 of these insects to start, and the growth rate is 6%. Technically, to do part A, it says determine the number of insects at 0 days. Technically, I'm plugging in 0 for the t, and I'm solving for the number of insects at the beginning. So I'm going to do that on my calculator. I'm going to go 500 and then second ln 0.06 times 0. Close out my parentheses. I don't know if you can see that. But so I tried to type 500 times e to the 0.6 times 0. And I'm going to hit enter. It gives me 500. It's always the number to the left of the e is the initial population. And this didn't say anything about millions of insects, so there's just 500 insects, whatever kind of these are, is the initial beginning population. So determine the number of insects at t equals 0, 500. What's the growth rate? It's always that number as a percent, so the growth rate is going to be 6%. So A, B, and C of number 4 are a lot like A, B, and C of number 2. They didn't really require any algebra. Part C, what's the population after 9 days? 9 stands for a t, because in this case the t's in days. I'm going to go P of 9 equals 500 times e to the 0.06 times 9, and use my calculator. So again, I pull this out, 500 second ln 0.06 times 9, close out my parentheses, and I'm going to round to the nearest whole number because you can't have a fractional insect. So I'm going to say 858 of these bugs, whatever they are, and that's going to be the population. So they're going from 500 of them to 858 of them in 9 days, according to this formula. The next 2 parts are going to require algebra, if there are 2 parts. Maybe there's only 1, but I imagine there's 2 parts. And in order to do the algebra, I still have to have the formula. Yeah, so part D, I still need this formula, P of t equals to 500 times e to the 0.06 t. This asks me, when will the population be 10,000? And in order to do that, I'm going to answer the question when. I'm going to plug 10,000 in for the left side of the equation, and I'm going to solve for t, and the t is going to stand for days, so I'm not going to say in a certain year. I'm not going to take this number and add it to 2012 because this is just a number of days. So it's not appropriate to write a yearly answer here. To solve this, I'll divide both sides by 500. On the left side, 10,000 divided by 500 gives me 20. So I get 20 equals e to the 0.06t. I'm going to take the natural log of both sides. I'm going to leave the left side at the natural log of 20. The right side, I'm going to write 0.06t times the natural log of e. But the natural log of e is 1, so I don't need to write it. So I can write this as the natural log of 20 equals 0.06t. Now I divide both sides by 0.06. The right side, I get my t because the 0.06 cancel. Left side, I want to round to 2 decimals, so it's going to be a fraction of a day. And it's an ln of 20 over 0.06. And I get 49 point, I'm going to round that to 93 days. I get 49 point, just can't see this, 49.928. So I'm going to say 49.93 days. So just under 2 months. How many? That's like 7 weeks for the population to go from 500 of these bugs to 10,000 of these insects. 4e is similar. It wants to know how long it's going to take the population to triple. Well, the initial population, or the beginning population, we did in part A. The initial population was 500. To triple, I want to find out when I'm going to get 1,500 of these bugs. I'm going to take those numbers and plug them into the formula. So I'm going to plug in 1,500 for the population. I'm going to leave the other half of the formula just the way it was at the beginning. I'm going to divide both sides by 500. This is going to give me 3 equals e to the 0.06t. I'm going to take the natural log of both sides. I'll leave the left side the natural log of 3. I'm going to rewrite the right side 0.06t times the natural log of e. But because this natural log of e is equal to 1, this is 0.06t times 1, so it's just 0.06t. So I can write this as the natural log of 3 equals 0.06t, and then divide both sides by 0.06. And I'll use my calculator. Left side is the calculator, right side, this 0.06 is cancel. So now I just go natural log of 3 divided by 0.06, and I get 18. This is round to 2 decimals, so 18.31 days. So the answer to 4e is going to be in 18.31 days for the population to go from 500 to 1,500. Just in case on that part D, I trimmed off the bottom, just in case you didn't see this 49.93 because my paper started kind of working its way down. That's what D looked like, just in case I flipped off the bottom. 6 is a similar problem. It talks about caffeine, and this is a realistic problem because I created this myself because I knew something about how caffeine is, digested or consumed. So this is a formula that tells me, like, if I take in 100 grams of caffeine, how much caffeine is going to be left in my body after so many hours. So I gave a formula and I said, this tells me how caffeine leaves the human body, and this P0 stands for the amount of caffeine that you consume. And the number in the exponent, the negative 0.139, once you consume caffeine, your body starts using it up, and it's decaying. It's going, the amount of your caffeine in your body is going lower unless you consume more. So anyways, this formula can tell me, if you give me how much caffeine you've consumed and you give me amount of time, I can tell you how much caffeine is left in your body. So in this particular problem, it says, what is the decay rate for caffeine? Well, the decay rate, or the rate of change, is this negative 0.139. The growth or decay rate is the number left of the t and the exponent written in percent form. So that it's going to be negative 13.9% is the decay rate. And that's in hours. So every hour, 13.9% of the caffeine that you consumed leaves your body, or 13.9% of the caffeine that's left in your body goes away. So that's an hourly decay rate. How much caffeine will be left in my body after 21 hours? That 21 is T. It stands for time in hours. And for this particular problem, the P naught, the P sub 0, the quantity that goes into the left of the E is 100. I didn't give you that in this problem. For this particular problem, the initial quantity of caffeine was 100 milligrams. I put that initial quantity to the left of the E. P sub 0 means the initial quantity. And then in for the exponent in this problem, I'm going to put negative 0.139 and then times 21 hours. So after consuming 100 milligrams of caffeine, which is probably just a coffee or a couple cans of Coke, how much will be left in your body after 21 hours? I'll go 100, and then second ln negative 0.139 times 21. And it says after 100 hours, there's only going to be 5 point, and this, does it tell me where to round? Round to 2 decimals. All right, 5.398, which is 5.40 grams left. So most of it's gone. After 21 hours. C is going to be the algebra part. Part C wants to know when 10 grams of caffeine will be left. And part D is tricky, but we'll get to that. Part C, when will 10 be left? Well, the formula for this particular problem should be P of T equals to 100, because we started with 100. And times e to the negative 0.139t. I want to know when 10 grams are going to be left. I'll put 10 in for the left-hand side of the equation and solve for t. To solve for t, I'm going to divide both sides by 100. I can actually do that left side in my head. That gives me 0.1 equals e to the negative 0.139t. Just like the rest of the problems I've been doing, the algebra is the same. I'm going to take the natural log of each side. I'll leave the left side alone. On the right side, I'm going to make the exponent of negative 0.139t a coefficient. The natural log of e is equal to 1, so this gives me the ln of 0.1 equals negative 0.139t. And then I divide both sides by negative 0.139. When I do this, I get calculator time. Go the ln of 0.1 divided by 0.139, and that gives me, and I wanted to round to 2 decimals. Oh, I forgot the negative. I go ln of 0.1 divided by negative 0.139, and I get 16.5. I'm going to round that to 7. So 10 grams will be left after 16.57, and my time is in hours for this function. So the answer to part C is going to take my 100 grams will go down to 10 grams in 16.57 hours. I think you do half-lives in chemistry, and you might do them a little bit different because they get into moles and insanely difficult stuff, but this is somehow related to that, but in a way easier form of that. 6D says, what's the half-life of caffeine? Half-life is the amount of time it takes to lose half the initial quantity. So for this particular problem, because my beginning amount is 100 grams, I want to find how long it takes to get down to half of 100 grams or 50 grams. For this particular problem, I'm going to put 50 into the left-hand side of the equation because I started with 100 grams. I want to find out how long it takes to lose half of it. And that's the implied computation in number 6. So when it's asking for half-life, it's asking for how long does it take for half of the initial quantity to be left or half to be gone. So half of 100, which is the initial quantity, 100 grams, I put in half of that, 50 for the left-hand side of the equation. I'll solve for t. On the left-hand side, you get 0.5, or 1/2 when you do the division. On the right-hand side, you get negative e to the negative 0.139t. I take the natural log of each side. This gives me the natural log of 0.5 equals negative 0.139t times the natural log of e. The natural log of e is 1, so I get the natural log of 0.5 equals negative 0.139t. Divide both sides by negative 0.139. Divide it by negative 0.139. Right side gives me the answer, or t, and then whatever this side comes out to, I'm going to round to 2 decimals, and that's how long it's going to take for half of the 100 grams to disappear or be used up by my body. So I'm going to go the ln of 0.5 divided by negative 0.139, and when I do that, I get 4.98 or 4.99 hours. So this is the half-life of caffeine. It's about 5 hours according to this formula, assuming this formula models reality. I think it's reasonably close. I actually think the half-life is more like 6 hours in reality, but this is got to be good enough. I mean, it's reasonably accurate. Maybe it's completely accurate, and I don't know the half-life of caffeine properly. So that's that problem. These problems are the nicer problems. They kind of hold your hand. The next problems are the tough problems. All the way through the rest of the problems that we're going to do, 8, 10, 12, and 14 are all hardish problems in that they're written and not in a very nice way. They give me the generic formula without the growth rate. So each one of these problems, 7 through 10 and 11 through 14, they're going to be 2 steps to get to the answer. The first step is to use as much of the first sentence as I can to solve for k. So there's enough information in the first sentence or the first 2 sentences to transform the equation a little bit. So for this particular, there's a bacteria culture and it's growing, and in 3 hours it grew from 500 to 1,500 bacteria. The question is, how long will it take the population to get to 10,000? I need 2 steps to do that. I don't have a very nice formula. The formula needs the initial amount and the growth rate. I know the initial amount, but I don't know the growth rate. I need to get the growth rate first. So first, I'm going to solve for k to get the k for the formula. I have this amount. The initial quantity is 500. So I know that this formula should be p of t equals 500 times e to the kt. I just don't know what the growth rate, what rate causes the population to grow from 500 to 1,500 in 3 hours, and I'm going to solve for that. What I'm going to do is I'm going to plug 500 in for the initial amount, 1,500 in for the future amount, 3 for the number of hours. So what I'm going to do is take that first sentence that says my population starts at 500, it grows to 1,500 in 3 hours. E to the k times 3. So this says 1,500 equals 500 times e to the k times 3, because 3 was the amount of time, and times in hours. So I can rewrite this as 1,500 equals 500 times e to the 3k, because it takes 3 hours to grow from 500 to 1,500. I'm going to solve for k, and it says round k to 3 decimals. So I'm going to solve for k by dividing both sides by 500. I get 3 equals e to the 3k. I'm going to take the natural log of both sides. I'm going to get the natural log of 3 equals 3k times the natural log of e. The natural log of e is 1, so this gives me the ln of 3 equals 3k. So k is the ln of 3 over 3. I'm going to round that to 3 decimals. So I'm going to go the natural log of 3 divided by 3 is 0.366. And that's what I'm going to use for the k. So into this formula, I'm going to write this as P of t equals 500 times e to the 0.366 t. So for this particular bacteria colony that I'm dealing with, the initial population was 500. To grow from 500 to 1500 in 3 hours, the k has to be 0.366. That k is constant for this bacteria colony. So that's part 1. I used the first sentence and did a bunch of algebra to solve for k, rounded to 3 decimals the k because my instructions say round the k to 3 decimals. Now I can answer the question, how long will it take for the population to reach 10,000? I'm going to use the formula that I have now and plug 10,000 for the future population. So I'm going to put 10,000, the future population, I'm trying to find how long it takes to get there, equal to the 500 that I start with times the growth rate, e to the growth rate times t power. Solve this. I divide both sides by 500. I think you get 20 on the left side. 10,000 divided by 500 gives me 20 equals e to the 0.366 t. Take the natural log of both sides. I get the natural log of 20 equals 0.366 t times the natural log of e. The natural log of e is 1, so I get the natural log of 20 equals 0.36 t. I divide both sides by 0.366. So I get natural log of 20 over 0.366 equals t. Calculator time, natural log of 20 divided by 0.366. I get 8.185. So it's around this to 2 decimal places, so I'm going to put 8.19. So t equals 8.19, assuming you could actually semi-see that. This doesn't get better. So I did natural log of 20 divided by 0.366 and got 8.185, which is 8.19. And this population is growing in hours. So it's the answer to the whole question is it's going to take 8.19 hours for this population to grow from 500 to 10,000. Took 2 steps to get there. That first step to tell me that the k equals 0.366 doesn't need to be in my answer. The whole answer to number 8, the population will grow to 10,000, whatever they are, bacteria in 8.19 hours. And even though I had to do a computation to find a k so I could use the formula like I've been using the formula, that k work doesn't go in my answer. So each of the problems between 7 and 10 and then again 11 and 14, they give me a generic formula with an initial population, but they don't give me a k, but they give me information to solve for k. The first step in the rest of the problems in this section is going to be to solve for k, and then create the formula that I need, and then answer the question. So 10 is the same sort of problem. I have a city that's expected to double in population in 20 years. The city currently has 1,000 residents. This bit of the problem is going to help me solve for k. And then the last bit of the problem is the question that I need to answer. Ultimately, I want to know how long it's going to take the population to grow to 1,000 residents. First thing I'm going to do is solve for k. I'm going to take this generic formula, the future population equals the initial population times e to the kt power, and put the information that's embedded in the first 2 sentences. First thing I see is the city has 1,000 residents. That's going to be the P naught, or the initial population. The 20 years is going to be the T that I'm going to use for the solving for K. And the population is expected to double. The future population that I'm going to use is doubling 1,000 to 2,000. I'm going to take those three values, plug them into this formula, and solve it for k. And then I'm going to come up with an equation. P of t equals to the initial population, 1,000, times e to the something times t, and that's the k that I'm going to get. It's going to be a positive answer because the city's growing. So I'm going to put these numbers into the formula. I'm going to go 2,000 equals 1,000 times e to the k times 20. I'm going to divide both sides by 1,000. This is going to give me 2 equals, and instead of writing k times 20, I'm going to write 20k. I'm going to take the natural log of both sides. This is going to give me the natural log of 2 equals 20k times the natural log of e. The natural log of e is 1, so this gives me the natural log of 2 equals to 20k. I divide both sides by 20, and I get k equals, and I'm asked to round k to 3 decimals. K is the natural log of 2 over 20. So I'm going to go natural log of 2 divided by 20. I get 0.035 for what I'm going to write for k. So I did natural log of 2 divided by 20, and I get 0.035. Rounded to 3 decimals as instructed. So 0.035 is, I just can't really, that's a good spot. So the k is 0.035. So in this, the formula is going to be the initial population, which is 1,000 residents, times e to the k, which is 0.035 times t. So that's the whole stuff that I have boxed in red allowed me to get a value for k, and it gave me a value for the initial population. The question that I need to answer is how long will it take the city to get 5,000 residents? To do that, I'm going to plug in 5,000 for P of t, and I'm going to solve for t, because how long is t? To solve this, I divide both sides by 1,000. I get 5 equals e to the 0.035 t. Take the natural log of both sides. I get the natural log of 5 equals, and I bring this up front, I get 0.035 times the natural log of e, 0.035t times the natural log of e. Because the natural log of e is 1, I get natural log of 5 equals 0.035t. Divide both sides by 0.035 and break out my calculator. It's going to take me to my answer. So I'm going to get t equals to, now I do the natural log of 5 divided by 0.035. And that gives me, it says round to 2 decimals now, 45.98. And the population is growing at a yearly rate, I think. Yeah, because the years. So it's 45.98 years. So it's going to take this city 45.98 years to get to 5,000 residents, because it's only growing at 3.5% per year. So the answer to number 10 is going to be 45.98 years. And even though I had to do all this computation to get a value for k to plug in the formula, that value doesn't go in my answer. The only thing that goes in my answer is the final t, because that's the only question, is how long will it take to get to 5,000 residents. It's 45.98 years. 11 and 12 and 14 are similar. I'm going to do them exactly the same way. The only difference is that this is a decay problem as opposed to a growth problem. So I'm talking about an element that's decaying, and this first sentence, just like the first sentence in our first 2 sentences sometimes, and the beginning problems, is going to help me get started. I need to take this equation that's given and come up with a value for k. And very specifically, it says the half-life of a certain element is 100 years. That t, that 100 years is going to stand for a t. And then it says a 40-ounce sample is given. That 40 ounce is going to be the beginning amount, and that P0 is the beginning amount. T is the time. And then when it says half-life is 100 years, that means if I start with 40 ounces of the sample, which is pretty heavy, that in 100 years, or P of 100, I'm going to have half of it. I'm going to have 20 grams or 20 ounces left in 100 years. So the numbers I need to solve for K are T equaled 100, the initial quantity equal to 40, the quantity in 100 years equal to 20. Ultimately, my formula for this is going to be P of T equals 40 times E to the something times T. So the 40, the initial quantity, is going to go next to the E. The value that I solve for K, which should be negative because this is decaying, is going to go in the exponent next to the T. So I'm going to plug these values in. I'm going to get 20 equals to 40 times E to the K times 100. Divide both sides by 40. This is going to give me 0.5 equals E, and I'm going to write this as 100K. I'm going to take the natural log of both sides. On the left side, I get the natural log of 0.5. On the right side, I get E, I'm going to get 100K times the natural log of E, making this in front of that. The natural log of E is 1, so this gives me the ln of 0.5 equals 100K. I divide both sides by 100. I get my K isolated, but I need to round to 3 decimals. I use my calculator, do the ln of 0.5, divide it by 100. I get negative 0.007 if I round that to 3 decimals. I knew it had to be negative. If it didn't come out to be negative, I've messed up because it's a decay. I'm not growing, I'm losing quantity. So this rounded to 3 decimals, negative 0.007 is what I plug into the formula. So the formula is P of T is the 40 ounces that I start with times E to the negative 0.007 T power. Now I want to know how long it's going to take, so there's only 10 ounces left. I start it with 40. I think it's just going to be 200 years. But let me do the algebra. I'm going to plug 10 in for P of T, and I'm going to solve for T. So I get 10 equals 40 times E to the negative 0.007 T power. I divide both sides by 40. I get 0.25 equals E to the negative 0.007 T power. Take the natural log of both sides. I get the natural log of 0.25 equals negative 0.007 T times the natural log of E. The natural log of E is 1, so I get the natural log of natural log of 0.25 equals negative 0.007 T. Divide both sides by negative 0.007. And right side is going to give me my answer in years. And left side calculator. Do the natural log of 0.25, divide it by negative 0.007. I doubt that you could see that. And when I do that, and do it properly, I get 198, and it says round to 2 decimals. So 198.04 years. So it's close to 200. It's not exactly 200 because this number is rounded. So the answer to part 12, or question 12, it's going to take 198.04 years. And again, because my K is rounded, my answer isn't exactly. The more decimals I carry with the K, the more exact my answer is. Last problem. Same problem, different numbers. Half-life of an element, still 100 years. I have 10 ounces. How long will it take? So 2 ounces are left. Exactly the same start. I'm going to solve for K just like I did in the last problem. I'm going to take my initial quantity at 10 ounces. My time is still going to be 100 years because it's still 100 years. And it's half-life, so my future quantity, my quantity after 100 years is going to be 5 ounces or half the 10 ounces. I'm going to plug those into the formula and solve for K, and eventually get the formula P of T equals the initial quantity 10 times E to some power. There's going to be a number to the left of the T. That's what I get here. That's the K. So here I'm going to go 5 equals 10 times e to the k times 100. Divide both sides by 10. I get 0.5 equals e to the 100k. Take the natural log of both sides. I get the natural log of 0.5 equals 100k times the natural log of e. The natural log of e is 1, so I get the natural log of 0.5 equals 100k. Divide both sides by 100. Get the k on the right side. Use my calculator for the left side. Round to 3 decimals because my instructions say to do that. So I'm going the natural log of 0.5 divided by 100. And that gives me negative, same one, negative 0.007 again. No, maybe that's not, because it's 100 years half-life, that's going to be a constant, I guess. Negative 0.007. So I'm going to go negative 0.007 next to the t. It's the half-life that made this happen. The quantity of the material made no difference. So since the half-life didn't change, the k didn't change. Now I'm going to answer the question, how long will it take till 2 ounces of the sample are left? So I've used everything in the first sentence, or 2 sentences, and now I'm going to put in 2 for the future amount, and get 2 equals 10 to the e to the negative 0.007 t power. Divide by 10. 2 divided by 10 is 0.2. I get 0.2 equals e to the negative 0.007 t. Take the natural log of both sides. I get the natural log of 0.2 equals negative 0.007 t times the natural log of e. The natural log of e is 1, so I get the natural log of 0.2 equals negative 0.007 t. Divide both sides by negative 0.007. Use my calculator. It's going to give me my answer. It's in years because the half-life is a yearly half-life. So I go the natural log of 0.2 divided by negative 0.007, and I get 229.92 years. So the answer to question 14, how long will it take the 10 ounces to decay to 2 ounces? It's going to be 229.92 years. And that's all that's needed. I needed this 2 columns worth of work to get down to that number, but the value for k that I came up with doing the computation isn't part of the solution. It's a necessary step. You need the k to get the answer, but it's not part of the answer. So one more section of word problems coming. They're heavy calculator, they're regression problems, and they're maybe comparably difficult. There's one thing that makes them maybe slightly harder, but there's a shortcut to make the slightly harder part not that hard.